Okay guys, today I'm gonna divide this lecture into two. So the first we're gonna be explaining Boolean algebra, talking about Boolean expressions, logic diagrams and truth table, and how to find each one from the other, and then we're gonna go on the next lecture. We're gonna go into simplification, Boolean algebra simplification, and we're going to take two ways, using the identity rules and using K maps. And this, I think, it will cover mostly everything we took in Boolean algebra. It's good for both computer organization class and the foundation class, so please review it. If you have any question, let me know. So now let's start. What's Boolean algebra? What's algebra? Mathematical system for manipulating variables that can have one of two values. In algebra, we have from 0 to 9. We have many values. We have not two values. Here in computers or in Boolean algebra, bool, what does bool stand for? Bool, true or false, two values. Either true, 1, or 0, false, either on or off. Binary, 0 or 1. That's why they call it Boolean algebra. And we use for it different Boolean algebra operators, and we're going to cover them in the next slide. We can describe the behavior of any circuit by, and here what do I mean by circuit? What's a circuit? A circuit is, for example, like a CPU, FPGA, GPU, a small tablet, cell phone. All those, they have circuit. Gates are considered, or can be considered also, a circuit. A circuit is a collection of gates which implements a special task. For example, if you do, let's say you take an example in C++, a program in C++, a program that calculates the average grade for a student. This program can be done in hardware on a circuit, meaning I can design it from gates and make a circuit, implement a circuit that will calculate the average grade of a student, and this will be faster than software. Remember, what's the difference now? Programming in C++ or Java or C, all that converts to binary, 0, 1. This converts to a circuit is a collection of gates. We have 6 gates we're gonna cover, but some people say there's 7 gates. They consider the XOR and N XOR, which is the NOT for the XOR, as 2 gates. Honestly, I don't go with that. I prefer using only 6 gates. If you want to use the NOT XOR, we'll put a NOT on it. So from those 6 gates, I implement any circuit. A circuit, collection of gates. What are gates now? Where did I get gates from? A gate, we can have, we're gonna see them, the AND, OR, NOT, NAND, NOR, and XOR gates. Those are a collection of transistors. What's a transistor? It's a switch, on, off, 0, 1, basic building block of any circuit, electrical device, logic device, digital device. Those, they all mean the same meaning. Circuit is 0, 1, true or false, which is a transistor. Base building block is a transistor. So let's see, we can describe the behavior of any circuit or logic gate or digital device in 3 ways. A Boolean expression, an equation saying what? A and B or C. Those are all Boolean expressions. Or we can implement it as logic diagrams by what? Connecting the logic diagrams for the 6 gates. We're going to take this. Or a truth table which lists all possible input and output for that circuit or for that gate. So let's see now. gates. Boolean expressions are created by performing operation on Boolean variables. What's Boolean expressions? Expressions that take Boolean, binary, 0, 1, true or false, operands. What's Boolean variables? They're variables that can have a value of 0 or 1, true or false only. They can't have any other value. Boolean operators, or what they call gates, or we're going to be using gates for Boolean operators, include the NOT, which is an inverter. I input a 0, I get a 1, or we can call it the sum, and which can be called as a product, NOR, NAND, and XOR. NOR and NAND are the invert of OR and AND. The invert of OR and AND, and XOR, where I have, if the inputs are the same, my output is 0. If the inputs are different, my output is 1, and we'll take an example on that also. XOR is used, if you know the CARC, cycle redundancy check. When I do a long division using binary, it doesn't do subtraction. What does it do? It does the XOR. A Boolean operator can be completely described using a truth table or a logic diagram or a logic. The Boolean operator AND, known as a Boolean product. The OR operator is the Boolean sum, known as the Boolean sum. So this picture is really important, guys. It covers what? The Boolean expression, the logic diagram, and the truth table of my 6 gates. 1, 2, 3, 4, 5, and 6. You have to know this. You have to know it. So I'm gonna start with the first gate. I have X. Boolean expression is X naught. This is a NOT gate. This is the logical diagram. This is my logical diagram here, and this is my logical expression for a NOT. If I have, and this is the truth table, and this is what the truth table means. If I have an input of 0, if X is 0, my output is 1. If my input is 1, my output is 0, the invert. And now I have the other case where I have what? The OR gate. What do we have for the OR gate? We have X or Y. This is the truth table, this is the logic diagram, and this is the Boolean expression. 3 ways to describe any circuit. Boolean expression, here's the Boolean expression for the OR operation or the OR gate. Here's the logical diagram for the OR, and here's the truth table for the OR. And remember, we said the truth table, which represents all possibilities of input and output. So what do we have as input? And here I have 2 inputs, X and Y. So how many possible outputs can I have? How do we calculate that? We do 2 to the power n, where n is the number of inputs. So 2 to the power 2 is gonna give me what? 4. And here I have 4 possibilities. And what are they? I'll start with 0, 0, which represents 0, and 0, 1, which represents 1, 1, 0, which represents 2, 1, 1, which represents 3. So 0, 1, 2, and 3. This is the best way to do it. So if I have 0, 0, 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. Think of it as sum. Now the AND gate. I have an AND gate. This is the logic diagram. This is the Boolean expression, and sometimes you can find it as a dot here in between those. And I have the truth table, which represents all possible inputs and all possible outputs. There's no way you're gonna get all those together, but in one instant in time you're gonna have what? This as an input 0 0. The gate will give you output 0. You're gonna have 1 1. The output will give you 1. Think of it as a product. 0 1 is 0, 1 0 is 0. So we took that. Now the NAND gate. The NAND is the NOT of the AND. What do I mean the NOT of the AND? The invert. If I add what? Let's see here. If I have a NAND gate, does it draw here? Okay, no. If I draw a NAND gate and put a NOT to it, it's the NAND gate. And here's the Boolean expression. And here, remember, we can have a NOT, a product. And this is the complement, the inverse, the bar here. And it goes over both of them. X dot Y, both of them under the bar. All. This is the NAND gate, takes two input possibilities, and it's gonna be the invert of an AND. So I have 0 0 as 1, 0 1 as 1, 1 0 as 1, 1 1 as 0. Be careful to this, guys. We can implement it in another way, having the invert here and using an XOR instead of using an AND. And this applies from De Morgan law. De Morgan law, what does it state? If I have a complement, I distribute the complement on X and Y. So I distributed the complement here, and we changed the sign. So it was a AND, now it's an OR. Both of those are equal. Both of those are equal. Both of those logic diagrams are also equal. Both of them will give us the same truth table. And honestly, I prefer using this one, the AND NAND. Now we have the X NOR. It's an OR with an inverter, an OR with the NOT gate. And from De Morgan's law, what can I do? Distribute the complement. I distribute it and I change the sign from what? From OR to AND. So both of those are equal. I prefer it this way. This is using an OR, this is using an AND by inverting the input. And here's the possible outputs. 0 0 is gonna be the inverse of what? Of this. So I'll have 1 0 0 0. This is the inverse of the AND. 0 0 1. The XOR and here's the where they use a plus sign inside a circle, the OR gate with this extra like a curve XY, my inputs. So this is this is the Boolean expression, logic diagram, truth table, which represents again all possible inputs and all possible outputs. Possible inputs, I can have 0 0, this will give me 0, 1 1, this will give me, so an XOR, if we have the same inputs, it's gonna give me a 0, different inputs, it's gonna give me a 1. That's the easiest way to know it, an XOR. So now let's take examples on that. Find the logic diagram and truth table for the following expression. What do I have? X and Y, parenthesis, X complement. This means I have a complement here. Think of it as if I have a complement here, the quote, or Z. So now let's see how we can draw this. And I use this website, it's really nice, .com, and we have the gates and we can draw what, but let's and I think we had x, y, and we have x complement or z. Was it? Did we have I have 3 inputs, x, y, and okay. So we're gonna find what? We're gonna go and find the logic diagram and the truth table. Can I change the size of this? We can do this as well also. We can say this equals, which equals, if I distribute x, y, x not, or x, y, and z. If I distributed this, I'll get this. This will equal 0. Why? If I have an x, which is, let's say, a 1, and x naught, which is a 0, if I NAND them with each other, it's gonna give me a 0, regardless of what y is gonna stay a 0. If x was 0, x complement is 1, the inverse, so it's gonna always be 0. But I don't want to simplify now. I want to draw that circuit. I want to draw this circuit. I can simplify this and draw just this. We're going to talk about that in the next lecture. So I have an and what am I anding? X and y, those can be considered as input. It makes it look better. Okay. And those are x and y. Let's put x and y here, and we can connect them just this way. This is much easier than and we can connect this by using the connector and this. Okay, and here what's good in it, you can run it in this. We're not gonna do the run it now, but you can try it out and see. It's a really nice tool. So I did the x and y. Now I want to do z, x prime or z. So I'm gonna use an OR gate. Where's an OR gate? Here's an OR gate. I'm gonna use, because I'm using the x naught, so I want to put it there. So I'm gonna have another input, which is z. So let's think of this as z. Oh, z. And now I'm gonna get the x naught. So I can take one from here, but I need the NOT gate. I hate the NOT gate, it's too big, look. It's supposed to be the smallest gate and it comes out to be the biggest gate. I don't know why they did it that way. Anyway, it's a nice tool. So I have a NOT. I can connect it with this, and I can connect it with X. So now this would be not X, and this is X. So now I have this and I have this. I have this, the X and Y, and I have X naught or Z, this. There's an AND gate here in between them. So I'll use an AND gate. Another AND gate. And now I'm going to connect this with this. To run it and get an output, you need to add an output device and connect it here, and just so this is my logic diagram. This is my Boolean expression logic diagram. Now what do I need? A truth table. And how's my truth table gonna be? How many inputs do I have? I have X, Y, and Z. X prime is not considered a separate input because we can get it from X. So X and X prime is one input. So I have 2 to the power what? We added 2 to the power N, which is 3 inputs. This equals what? 8. So I'm gonna have a table of 8, and let's add 9 for, let's see how much it's gonna take. 9, so I can take what? The X, Y, Z. So here I'll put X, here Y, and Z. So now how do I decide? How can I pick my possible inputs? You can go either the hard way by figuring out, or you can put what? From 0 to 7, just represent it in binary. From 0 to 7. So first one is going to be 0. How do I represent 0 in binary? It's going to be 0, 0, 0. And I like to align it in the middle. Let's do and how do I represent 0? Then I have a 1. How do I represent a 1 in binary? In 3 bits, here is 1. And this represents a 2. And this represents a 3. This represents a 4. And this represents a 5. 4 and 1. And this represents a 6, and this represents a 7. From 0 to 7. That's the easiest way. I have 8 rows, 8 different possibilities. Now how can I get my output? Here we're going to have the first thing, X and Y. So I'm going to do both of those, and both of those. So what do I have? 0 and 0. Remember, think of it as a product. 0 and 0, 0, 0 and 1 is 0. 0 and 1 is 0. 1 and 0 is 0. And here's what I'm looking at. Each one I'm doing this. Now I have 1 and 0 is going to be 0. Now I have 1 and 1 is going to be 1. 1 and 1 it's going to be 1. Now I need to find what? X naught plus Z. But first I need to find X complement, which is the invert of this. So it'll be what? 1, 1, 1, 1, 0, 0, 0, 0. And to make sure you're going the right way, see the pattern? Here I have 4 zeros, 4 ones. Here I'm gonna have 2 zeros, 2 ones, 2 zeros, 2 ones, 1 0, 1 1. If I had another input, it's gonna be what? 8 zeros, 8 ones. See the pattern. So now I need to find x na plus z, which is and I like to do this so we can know which ones we're working on, so we don't do any mistake. Remember, one mistake will be costly in this. X na or, so an OR is a sum. 0 or 1 is 1. 0 or 1 is 1. 1 or 1 is 1. 0 or 1 is 1. 1 or 1 is 1. 0 or 0 is 0. 1 or 0 is 1. 0 or 0 is 0, and 1 or 0 is 1. Now I need to find what? X, y, ANDed by x prime or z, and I already have what? The x and y, which is this, and I need to find AND it with this. So an AND is a product. 0 and 1 is what? 0. 0 and 1 is what? Is another 0. 0 or 1 is what? Is another 0. 0 and 1 is another 0. 0, 0, 0 and 1. So this is my truth table, which represents all possible input and all possible outputs, and here I have my logic diagram, and this is my Boolean expression. 3 ways to describe any circuit, any logic circuit, any logic device, any digital device, any electrical. Remember, all have the same name. Now let's go and see. Now here's another example. Find, okay, so the first one I got a Boolean expression, and I found what? Logical diagram and truth table. So now what if I give you the logic diagram and tell you what? Sketch the table and give me the Boolean expression. Let's see this. What do we have here? Where do we start with? Are we gonna start with this or this or this or this? Usually I prefer starting from lower and going up. So here, what's this? I'm gonna have an OR, and let's write it here to make it easier, not go there, and then I'll copy it and paste it. So I have an C ORed with not B, C ORed with B not. This is whatever is coming from here, which is this, ORed from this one with what? What's this? I have A and B. A and B. And now all this is what? XORed. Oh, now I'm gonna write the XOR. We have the XOR here. Okay, we can use this. We'll use this text. I'm gonna use this, and I put it, and I'll put a plus sign inside it. And I'm gonna put it later, so because now it's not gonna allow me to write anything after the OR. I'm XORing this, so I'll put this here, and I'll XOR it with what? With whatever I have here, which is what? A not NANDed with B. A not with NANDed with B. So how did we represent? If you go here, how did we represent a NAND gate? X and Y both complemented. So I have A not and B both complemented. A not, and don't let the A complement confuse you. So this is gonna be A not and it with B, and both of them complement or NANDed, or we can say okay. Come on. This is the XOR between this and this. Sorry, it looked like that, but it's 1 gate, 2 gate, 3, 4, 5. This is not considered because it's with the NAND. This is a gate, this is separate, and this is separate. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 7 gates. 1, 2, 3, 4, 5, 6, and the AND is 7. So now I need to draw the truth table for this. How many inputs do I have? Don't let the complements confuse you. I have 3 inputs. So I'm gonna have the same thing here. I'm gonna have 2 to the power 3, meaning 8 possibilities, 8 inputs, and let's change this back to Y. And this back to gray. So I have what did we have? A, B, C, or what did we use? A, B, and C, and I'm gonna represent from 0 to 7. So what's 0? 0, 0, 0. Now I'm gonna represent the 1. 1, 0, 0, and now I'm gonna represent the 2 in binary. Remember, there's 2 in binary, this is 3 in binary, this is 4 in binary, and this is 5 in binary, and this is 6 in binary, and this is 7 in binary. And what was my equation? Did I copy it? Okay, and here we have the, don't forget the XOR, guys. 1 minute, let's make space. This is my Boolean expression, and I need a small XOR. There might be a way to do it in another way. Okay, come on. And I'll put a plus sign inside it. Make it larger, so give it a bold. So I'm gonna start finding what? C or B naught. So the first thing I need to find is B naught, which is the invert of this, and I'm gonna have what? 1, 1, 0, 0, 1, 1, 0, 0, and now I need to find C plus B naught. I'm gonna find C ORed with B naught, so I'm gonna find this, and OR, we said it's, think about the sum, so 0, 1, or 1 is gonna be 1, 1, or 1 is gonna be 1, 0, or 0 is gonna be a 0, and 1 or 0 is gonna be a 1, 1, 1, 0, and 1. Now what do I need to find? A and B. A and B. What do I have? A and B. This. So I'm gonna find A ANDed with this. And think of it as a product. 0 and 0, 0. 0 and 0, 0. 0 and 1 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 0 is 0. 1 and 1 is 1. 1 and 1 is 1. Here's what I'm looking at, guys. Those. I'm calculating those ANDed together. And each one corresponds to 1 here. And here I have 1 because I only have those two cases where I have a 1, 1 and 1. The other is a product. Think of it. Anything you multiply by 0 is a 0. Now I can find this ORed with this. So I'm gonna have what? C or B not ORed with AB. And let's see here. So I'm gonna find this ORed together. And OR, think of it as a sum. So 1 or 0 is 1. Here's what I'm calculating. Now 1 or 0 is 1. Oh, 1, 0. 0 or 0 is 0. 1 or 0 is 1. 1 or 0 is 1. 1 or 0 is 1. 0 or 1 is 1. 1 or 1 is 1. Now I need to calculate what? A and B, and then what do I need to do? The whole result. Okay, so I need 2 extra columns, and I'm gonna insert 2 after, please. Now here I'm gonna have what? A, B, not, which is I have the A and I have the B not. So I'm gonna calculate this, and when they're not beside each other, I prefer to color them so we know the difference. Or I think this way you make less mistakes. So we said it's an AND. So an AND is like a product. 0 or 1 is 0. 0 or 1 is 0. 0 or 0 is 0. 0 or 0 is 0. 1 or 1 is 1. 1, 0, and 0. And now I need to do what? All of this. Meaning I XOR, and here's what I'm gonna do. C or B not ORed with AB. All of this is what? And I'm gonna do it as an XOR writing. So X ORed with AB not. So hopefully that's right. So now let's make those smaller. Take some of the gap over there. Okay, this is better. Now I need this XORed with this. So those two XORed. And what did we say an XOR is? An XOR where there's different, it's a 1. This is a 1, different, the same 0. This is 0, this is 0, 1, 1, 0. Okay, so this is 1, 1, 0, same, different, same, same, different, different. So now here's my truth table. So from a logic diagram I got my Boolean expression, here it is, and we got our truth table. From where? From this logic diagram. First example we took, if I give you a Boolean expression, how to get what? The logic diagram and the truth table. Second example was I give you a logic diagram and you give me a Boolean expression and a truth table. So now what if I give you what? A truth table and you should give me a Boolean expression and truth table. And remember guys that always it's better always to find the Boolean expression first. It makes it easy. I don't know here if you can do it in another way, but I don't think so. You can like get the logic diagram first and then it's gonna be no, I don't think so. No. But here's this. Sorry, this was added here. I did a video last night, but after I finished 2 videos I went back and checked and they didn't open with me, so I'm doing those again today. So let's check what do I have here. I have this table. I have 3 inputs. Those are all the possible values of those inputs, and this is the result or the function. What is it gonna output? So now how can I find the Boolean expression that represents this truth table? We go look at the ones, and we have 2 ways to do it. One way is using I should have divided this side into 2, but okay. You know, I can do that. 1 minute, real quick. Just want to change this thing. Okay. We look at the ones. Here I have a 1 in the output. Look at the output. First way we can do it as sum of product. Sum of product meaning what? Let's see what's sum of product. What do I have here? I took the output 1 and I'm gonna look at those. This represents A naught, C and D. A naught because it's 0. So sum of products is gonna be A naught, C and D. Here where the sum of products comes from, sum of products. And now I look at the next one in the output. I only look at the ones in the output, and I have what? 1 0 1, meaning A not C, D. A not C and D. Sum of products. Sum of products. Or of ands. Or of ands. I look at the next one. I only have 3 ones, so I'm gonna have 3 products summed together. What do I have? A, C, D. This represents A, C, D. Remember, the 0 represents the not of that value. So here I have A, C, D. So this is my one way to get a Boolean expression. This is a Boolean expression. How can I do it in another way? I can do it as product of sum. So I'll have what? I'll have sums and ands instead of and am I gonna have 3? Yeah, because I have 3 ones, I'm gonna have the same thing. So what does this represent? A not C D. So here I'm gonna have A not or C or D, product of some ands of ors. And here I'm gonna have the same thing. Look at the second one. I have what? A not A, C not and D. A, C not and D. And here I have what? This one I'm gonna take those three, which are A, C, D. And you can go back here. I'm not gonna draw it, but to save time, but you can go back here and draw this. The only problem we're gonna face here is this is an input. Here you can use a NAND gate with 3 inputs, but I don't have it this one. Let's do a new one. I don't have a NAND gates with 3 input. So for this I can have here what? Let's see the equation. Back to the equation. Do it real quick. Do just one of those. So I have A not C and D, 3 inputs. How am I gonna put them here? You can put another input. An AND gate with 3 inputs, it can be, it's possible, but they don't have it here. I tried to change it, I couldn't, but here's what we do. We add another AND gate. So what would we do? I'll use here an A not, and here I'll have C, and I'll do it with D. So how does this go? I'm gonna have a not for the A, and see the not gate, how big it is. Okay, connect it to this, connect this to this, and this is gonna be A. So here I'm gonna have not A, here I'm gonna have what? C. I'm gonna connect it with this one here. So here I'll have A not ANDed with C, and I can add the result with what? With D. Or we can use a single 3 input NAND gate, but because I use this, I'm not gonna finish the table, the logic diagram. I just wanted to show you how it goes. So this comes here, so I'm gonna have 3 of those. You know what, let's draw them real quick. Well, I can't paste here, or did it paste it on top of it? Okay. Let's see what bring to front. No. Can't tell me you're not copying. Come on, what? Paste here. Okay, it's loading, sorry. Ooh. How many times did I paste? Just give me one. Or I need actually, oh, give me two. No, I don't want that part. Which part is this? Oh, why did it all? Okay, 1 minute. Undo. 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 Whoa, where did it go to? Why all that? Okay. So here, undo. Let's do a paste here. I'm just gonna finish it. I'm gonna do it all, and let's do another paste. We can connect all those inputs together, but because I did a copy paste, I'm gonna use different ones. So now for this, this is the first one. Here's the second one. I'm gonna change this A, and here let's put a D or a C, because I have not. So the C can use the not. I'm not gonna change that much in there, and I can end it with a G. Here I don't need this one, and I can leave this as is. Be careful. In this case, I'm leaving that one loose. So okay. So now I have this representing this, this representing this, and this representing this. And here I can use another 3 input OR gate. If I had a 3 input OR gate, I can put it here and connect them all. But now what do I need to do? I need to use 2. So here's what I do. I connect those two, okay, to this, and connect this to it. So here's what I did. I did both of those, or both of those. Now I OR them with this. I get another OR gate, and here's what OR it, and OR it with this one, and bingo, we're done. Here's our circuit. But remember, if we are different, we can have a 3 input OR gate, 4 input OR gate, 3 input NAND gate. We'll have less gates. We'll have 1, 2, 3, 4, 5, 6 with the knots. And here what do I have? 6, 7, 8, 9, 10. I had 6 there and 10 here, so that will be more efficient for sure. Now let's check what we can do. This one. Oh, not this one. I don't want this one. Where did it go? Let's close this one. Okay. So, and same thing, I can implement that with ORs instead of ANDs, and then ANDs. So we took 3 examples to how we can describe a circuit. First way was Boolean expression, logic diagrams, and truth table. Please guys, you have to know those. You have to know those. If you don't know those, I don't know how you're gonna draw out a logic diagram, or are you gonna do a truth table. So now let's stop here, and I'll come back in a minute for the simplification. Let's do it in another video and see what we get.